The human gut is far more than a passive digestive tube. It's an active surveillance system constantly scanning its environment, not only for nutrients but also for microbial activity. One of its most fascinating features is the ability to detect microbial movement, specifically through the recognition of bacterial flagella, the whip-like structures that allow many bacteria to swim. This is accomplished through pattern recognition receptors like toll-like receptor 5, TLR5, which identify components such as flagellin, the protein that forms the flagella. This molecular recognition isn't just about immune defense. It has profound effects on digestion, satiety, and overall health. Understanding how the gut perceives microbial motion gives us new insight into how deeply intertwined our physiology is with the microbial world inside us. TLR5 is a sentinel receptor, primarily expressed on the basolateral surface of epithelial cells in the gut lining, as well as on certain immune cells like dendritic cells. Unlike other TLRs that recognize viral RNA or bacterial toxins, TLR5 is specialized. It recognizes flagellin monomers that are shed or exposed when bacteria move or replicate. This evolutionary design suggests that bacterial motility, their ability to swim toward or away from nutrients and immune threats, is a key indicator of microbial activity and intent, and therefore something the host must monitor closely. When TLR5 detects flagellin, it triggers a signal cascade through the NF-B pathway, activating the production of cytokines and antimicrobial peptides. This primes the gut's innate immune system to stay alert but not overreact. Importantly, in a balanced system, this response is moderate, more like a traffic cop than a riot squad. The gut tolerates many microbes, especially commensals, but the detection of movement may signal a shift, active colonization, invasion, or a microbial shift that needs attention. In this way, flagellin detection helps maintain intestinal homeostasis, not too much inflammation, not too little vigilance. But the influence of flagellin goes beyond immune readiness. Studies in mice have shown that TLR5 signaling affects metabolic health and food intake. Animals lacking TLR5 tend to overeat, gain weight, and develop features of metabolic syndrome, including insulin resistance. This suggests that flagellin detection may contribute to satiety signaling, either through immune-neural crosstalk or through the modulation of gut hormones. The working hypothesis is that when gut epithelial cells or neuropods detect bacterial motility through TLR5, they help inform the brain about the microbial environment. Is the gut in a stable, nutrient-rich state? Are microbes behaving as expected? If the signals indicate balance, the gut can safely transmit fullness messages to the brain, reducing the drive to eat. Flagellin-triggered TLR5 activation has also been linked to the release of hormones like GLP-1 and PYY, both key players in satiety and glycemic control. These hormones slow gastric emptying, reduce appetite, and improve insulin sensitivity. So, microbial motion through flagella can help orchestrate a coordinated digestive brain immune response, improve gut transit, signal satiety, and prepare the immune system for microbial shifts, all from a single protein receptor interaction. Moreover, the interaction between flagellin and TLR5 serves as a regulatory checkpoint for gut barrier integrity. When motile bacteria come too close to the epithelial surface, TLR5 helps trigger the production of tight junction proteins and mucins, reinforcing the gut's physical defenses. This prevents harmful microbes from breaching the epithelial barrier and entering the bloodstream, which could otherwise trigger systemic inflammation. In this way, flagellin sensing is not just reactive, it's preventive, helping to tune the immune system to respond without overreaching, a critical balance in a gut populated by trillions of potentially inflammatory organisms. In pathological conditions, such as inflammatory bowel disease, IBD, obesity, or certain infections, this balance can be disrupted. Either TLR5 is overactivated, leading to chronic low-grade inflammation, or it's underexpressed, allowing invasive microbes to flourish unchecked. Both outcomes demonstrate how crucial microbial motility sensing is to homeostasis. Interestingly, dietary components and microbiota composition can influence flagellin exposure. Diets rich in fiber and polyphenol tend to support microbial communities that express fewer flagellated, invasive traits, while high-fat, low-fiber diets often encourage the rise of aggressive, flagellated bacteria that provoke gut immune responses and may impair satiety. The long-term implication of these discoveries is profound. Flagellin, TLR5 signaling is not merely a molecular curiosity. It is a dynamic interface between microbial behavior and host physiology. It allows the gut to feel microbial activity, interpret it, and take appropriate action to protect, regulate, or adjust. By decoding this microbial motion, the gut doesn't just identify threats, it gathers intelligence that shapes hunger, immunity, and metabolic stability. In short, microbial movement is not invisible to the body, it's legible. And the gut, through receptors like TLR5, is constantly reading and responding to that script. As research progresses, therapies that fine-tune this interaction, whether through probiotics, engineered flagellin analogs, or TLR5 targeted compounds, may become powerful tools to restore metabolic and immune balance. What was once seen as background noise, bacteria swimming silently in the dark, may in fact be a crucial biological signal in the ongoing conversation between microbe and host.